chapter. So here we have the graph of sine, and you can see over on the left, we have this kind of like cast rule grid that we worked with, the 0, 90, 180, 270, 360 rotation. And then we have the actual periodic wave function on the right. So I want you to track this red line as this point rotates around, and you're going to kind of see the connection between the angle that you see inside this circle and the angle that you see over on the x-axis. And then you also see a connection between this red vertical line and where the point falls on this graph over here. So as I rotate around, you guys can just kind of take a look at what's going on here. Okay, so what are you observing is happening here? What's the connection between what's happening on the left and what's happening on the right? Jose, what would you say? Yeah, the triangle over here. Yeah, so we see the height of where the wave is matching the height of this red line of the triangle. And then, of course, we see the angle of rotation in this inner corner here, matching the angle of rotation as we go along the axis here. So basically, sine is going to track this vertical height of the point as it rotates around. We can kind of see, like, as that point gets lower, this wave gets lower. And then even as it goes into the bottom section here, once it goes below the x-axis over here, then the y's become negative on our curve over here. So that's the idea with sine. It's tracking the vertical height of a point as it rotates around. Let's look at cosine. So this is cosine. Again, I want you to track, like, as we rotate around, look at the angle and look at what is being tracked here as we go around. We're on lesson 4 right now. I'm just showing a visual so that we can take a look at what's happening. Jose, what do you see happening? Okay, so the angle of rotation becomes the x value of our wave function graph. So as we rotate around, if I change the angle here, so let's say I change the angle to 135, we're over at 135 on the wave function. And then we're actually tracking the length of this line now. In sine, we were tracking the length of the vertical part of the triangle. Now we're tracking the length of the horizontal part, or the x-axis distance of that triangle.
So would it be possible if you just turn it vertically? Well, because like you're basically doing x value. Do you know what I mean? Or
what do you mean by turn it vertically?
Like, you know how a sine function goes, like it's the y value, so it goes like over, like horizontally, right? No.
I don't know what you're saying.
Oh, right.
They're shifted versions of one another. Like, they're very similar, obviously, but I'm not sure what you're saying by turn it vertically. Okay. Okay, so we can kind of see, like, this pink line that's being tracked is the distance of this point from the middle. So as the point moves to the right, we go to the positive section of the graph, the wave function. As the point moves, like, to this side of the x-axis, because this is the negative side of the x-axis, we'll see the graph get below the y-axis, so we do a wave function. So the x-axis is the angle of rotation. The y-axis of cosine is tracking that horizontal distance of the point from the middle. So that's the deal with sine and cosine. So let's flip over to the lesson here. We're going to summarize this. Sine function is tracking vertical, where it's graphing, vertical displacement, versus the angle of rotation. As a point rotates around the unit circle, remember we talked about the unit circle in the last chapter. This also makes sense because what do we know about sine theta in terms of x, y, and r? What is sine theta equal to? In this last chapter. What is sine theta equal to in terms of like our x, y, and r values that we discussed last unit? Sine is y over r, and y is the vertical, right? So sine is tracking vertical. Cosine is x over r. Cosine tracks the x, which is the horizontal. So this is going to graph the horizontal displacement. And I'm just going to say versus, and then we're going to say ditto. Versus angle of rotation as the plane rotates around. Okay, and maybe we can just remind ourselves sine theta is y over r, so it deals with the y coordinate. Cos theta is x over r, so it makes sense that cosine would be dealing with horizontal if cosine is x. I just said it's just ditto, so just like the exact same thing that's here is repeated down here. I don't think we need to write it all out again, though. Okay, so sine, we're going to think vertical, cosine, we're going to think horizontal. Okay. All right, so when we think about application, we're going to be doing application in the first half of today, involving anything that rotates at a constant rate. And then in the second half of today, we're going to be doing applications that don't necessarily involve rotations. So they might involve time, something going at a consistent speed or something like that. So today we're going to take a look at like Ferris wheels. Those rotate constantly along the same track, usually around the same speed, same angles of rotation, obviously, as it rotates around the circle. Carousels. Can anyone think of any other circular objects that have something going around at a constant rate? A wheel? What was the? Okay, the wheel of a car could work. Yep. Anything else? Clock? Was it? It would have to be moving though. Something that's moving. Fan could work. Yes, that's good. Windmill. That could work as well. Okay, so anything that's kind of like rotating along the same track consistently, that can be modeled with all of these sine and cosine functions that we've been looking at. There you go, circle of life. Don't know how you would graph that, but yes. Okay, so let's take a look at a Ferris wheel to start. This Ferris wheel has a radius of 8 meters. It's turning counterclockwise. We're going to let the origin be the center of the wheel, and we're going to begin our sketch when the radius from the center of the wheel is along the positive x-axis. So our usual 0-degree elevation. Sketch the vertical displacement from the center of the wheel versus the angle of rotation for one complete rotation. Okay, so I'm going to create a circle here that's 8 units in all directions on our axis. Radius is from the center to the outside. So 8 units this way, 8 units this way, and all. So it's going to start here, and then it's going to rotate around from there, counterclockwise. Okay, so before we go and like do the actual rotation part, I want to just mark off these important pieces, these points right here. And I want to know what their coordinates are on the X and Y axis. So what's the coordinate of this point? If I go 8 units over on the X axis. 8, 0. Okay. What about this point? That is 0, 8. How about the point on the left? Negative 8, 0. And the bottom point? 0, negative 8. Okay, perfect. If we're graphing vertical displacement, are we interested in the X coordinates at these points or the Y coordinates? Or vertical displacement, the Y's. So I'm going to highlight all the Y's because that's what I'm interested in tracking for the vertical. So 0, 8, 0, and negative 8. That's what we will look at. Okay, here's the deal, guys. Wherever you start, you have rotated 0 degrees wherever you start. And then you will rotate from there. It won't always be at the normal 0 degree location. Now, in this case, it tells us that we are starting in line with the center on the positive x-axis. That actually, it describes that to us. So this is the start, and the start is always 0 degrees wherever you are. So at 0 degrees, what is the vertical displacement? What is the y there, Jose? 0. So that's going to be our first point. I'm going to just go by 2's here. 2, 4, 6, 8, -2, -4, -6, -8. And we're going to plot 0, 0. Okay, this is rotating counterclockwise, it says. So then I'm going to rotate up here. How far have I rotated angle-wise from where I started? We've now rotated 90 degrees. And at 90, what is the vertical displacement? 8. We're interested in just the y coordinates. So 98.
0, 0, and then start at 0, 0 or 0?
Yeah, 0, 0, and then 98. Okay, next one, if I rotate down here, I've now rotated 180 degrees from where I started. And we are horizontally in line with the center, right, Jose? So where are we? We're looking for the vertical, so it's at 0 vertical. So 180, 0. Okay, next one, we've now rotated 270. What's the displacement? We're now 8 units below the center, so we are at -8 at 270. Okay, and then we're gonna end where we started here. So this start position is 0 and 360. So now that we're at 360, we're back at a displacement of 0 because we're in line with the center. We're not above or below it at all. Okay, and there's our graph. Looks very similar to our usual sine function, except it just has a different amplitude. What do you notice about the radius of the circle? They're both 8. The radius of the Ferris wheel is 8, and the amplitude, if we look at the graph, is 8 units from the middle to the max and the middle to the min. Oh, did I graph this point wrong? I graphed it down 1 too far, didn't I? I did. I think I did. Yeah. Okay. So, yeah, technically, like if we continue rotating around on the Ferris wheel, it will continue. Not really, unless the Ferris wheel rotates backwards. I guess you could go into the negatives. Okay, any questions so far? This is tracking the motion. So basically this tells us like the vertical height or vertical displacement of the person in the Ferris wheel cart as they rotate around and tracking their angle of rotation. That's the motion. That's the graph that we can use to indicate what motion is happening as far as vertical displacement. So there's vertical displacement from the center, and then we're going to do some that are vertical displacement from the ground as well. So it depends. This is from the center, yes. Okay, so let's switch it up a little bit. Now we're going to sketch horizontal displacement from the center. Last time we did vertical. And this will be same starting point as part A. So I'm going to create a circle again, 8 units in all direction. And I'm just going to recopy those points down that we figured out above. So this is the point 8, 0, 0, 8, -8, 0, and 0, -8. This is going to be the start again, which will always be 0 degrees. So if I'm tracking horizontal displacement, am I interested in all the x coordinates at this location or all the y coordinates? Okay, so horizontal will be x's. So I'm interested in all of these coordinates as we rotate around. So at 0, are we in line with the center horizontally? Are we to the right? Are we to the left of the center? How many units? What does that look like? 0 degrees, where are we? At 0 degrees, are we to the right of the center, to the left of the center, or are we equal to the center?
Right.
We are to the right 8 units. So we're 8 units over. So if we do again 2, 4, 6, 8, we'll graph 0, 8 to start. So that's up here. Okay, we're still rotating counterclockwise. So I'm going to rotate to the next location. How far have we rotated from the start? 90 degrees. And now am I in line with the center horizontally? Am I to the right? Am I to the left? Where am I? I'm in line with it. I'm not to the right or to the left at all. So this will be 0. We can also see the x at this location is 0. Okay, next point will be 180 degrees from where we started. And we are 8 units to the left. So yes, -8. Put that on our graph. Okay, bottom point here. 270, correct. And then yes, we'll finish the same spot that we started. So this will also be the 360 point. So 360, we're 8 units over to the right. Is the second point always the coordinate I'm using? Yes. The second point is always the x value. So you're saying the y coordinate of what I'm graphing is the x coordinate. Yeah. Yes. So the x's are the degrees of rotation. The y's of our new function, we're tracking displacement. So we're tracking the x's as we go around. I know that's kind of confusing, but the y is representing horizontal displacement over the angle of rotation. Okay, so suppose we now switch this up one more time. Instead of starting at the usual 0 degree location, we're now going to start at the bottom of the Ferris wheel. And we're going to track vertical displacement on the next page. Can I scroll from this? Okay, so we're going to draw our Ferris wheel one more time, 8 units in all directions. Okay, and then I'm just going to plot those points one more time. So there's still 8 units in all directions. Because the radius is 8. If we change the radius, then it will change. Yeah, all the same question. Different scenarios though. So now the trip is going to be started at the very bottom of the Ferris wheel, which is this location right here. This is our start. At the start, we have not rotated at all yet. So the start is always 0. This is 0. And I'm looking for vertical displacement. So are we interested in the y coordinates as we rotate around or the x coordinates? Okay, so we're interested in all of these ones then. Okay, so first point, what is it going to be? 0, -8, because we're looking for the vertical displacement and we're 8 units below the center at this location. So 0, -8, we'll start down here. Okay, still rotating counterclockwise. How far have I rotated from where we started now? If I rotate up to this next point here, 90, 90 and 0, because now we're in line with the center. We're not above or below it at all. Okay, next point, how far have we rotated now? 180, and we're looking at the y coordinate at this location. We're now 8 units above the center. Johnny? Depends what it's asking for. This asks us for the vertical displacement versus angle of rotation. So that is why we're doing degrees for x and the vertical for y. So horizontal versus angle of rotation for the previous one. So the angle is the x, and then the horizontal displacement is what we're tracking with y. The horizontal displacement, so you need to think about like independent variable versus dependent variable. We talked about when you guys graphed like lines back in grade 9, you talked about independent versus dependent variable. The independent variable could be something like time. The independent variable in this case is the angle of rotation, because where I am on the graph depends on the angle of rotation, right? So that's an independent variable, the rotation. And then either the vertical or horizontal displacement is dependent on where the angle of rotation is, right? So that's the y. So you need to kind of think like, obviously the height is not going to be, the angle is not going to be dependent on the height. The height is going to be dependent on where you are around the circle, right? So that's the independent variable, angle of rotation. Georgia? Yep. Yep. It changes the whole graph of the function. Yeah, it shifts the graph. That's basically what it does. Okay, so I'm guessing you guys probably filled these in already. So 270 at 0. And then we'll finish at 360, -8. Okay, so I'm going to plot these. You'll see, Johnny, you'll see a couple other examples where we do like different things for X. Like in the next lesson, we're going to have no angles of rotation. It will be like time and different things like that. So you just have to, again, think about like which is dependent on which. X is always the independent variable and Y is the dependent. So this is what our graph should look like for this one. Questions so far? Or other questions, I should say? Okay. Carousel. Okay. Yeah. We're going to change it, yeah, because we're switching the location of where we start. We could probably just not even have them there to begin with, right? You decide where they are based on where you start. Okay, so let's look at a carousel. This one has a diameter of 15 meters. It rotates at a constant speed. A horse that is directly in line with the center horizontally, and I'm just going to add to this to the left, just so that we have a definitive starting point. It rotates around 3 times. Create a graph that models horizontal displacement from the center as the horse rotates around. And I'm going to add clockwise to this. I don't think it really matters because the answer will be the same either way, but let's just try it out with a clockwise rotation. Okay, so if the diameter is 15, we need the radius. We need to know how many units in each direction we go. What's the radius? Okay, radius 7.5 meters. So we're going to create a circle that's 7.5 meters in all directions. So it'd be very similar to our last one, just a little bit smaller. And then we can figure out what each of these points are on each of the axes. Nope. Other way around. 7.50. This one's 0, 7.5. This one will be negative 7.50 and 0, negative 7.5. Of course, is directly in line with the center horizontally, and I added to the left. So where is that starting position? Directly in line with the center to the left. Yes, so we're going to start here. This will be our 0 degree location. So we're going to ignore that 180 there. And then we're going to rotate around. I added to the end, we're rotating clockwise from here. So I might just go by ones on this so that we can get 7.5 graphed a little bit more accurately here. So starting location, we are graphing horizontal displacement. So am I interested in the X's as we rotate around or the Y's? Okay, so each of these ones are what we're looking at. So at 0, what is the X? What is the horizontal? -7.5. We're 7.5 units to the right or the left of the center. So -7.5. It's going clockwise.
90, 0.
Okay, yep, this will be 90 and then 0.
87.
Okay, next location.
3, 16, -17.
Yes.
Setting back something, 0.
Okay, so just looking at all the X locations as we go around here. So 360 will also end at -7.5. Now this one asks us for 3 rotations, so you're gonna have to extend the cycles. So I'm just gonna finish graphing here and then we'll do extra cycles. Make sure you're at in between 7 and 8, each of these. And then of course, every quarter that we rotate, we're rotating around 90 degrees. So as we finish our cycle here, the next cycle will start again immediately. So the next cycle, 90 degrees up, fall right at 450. And then I'm just going to continue 90 degrees from there and continue the pattern. So we'll go up to 7.5, 90 degrees later. And that's this part of the next cycle. Okay, and then 90 degrees after that, we're at 630. Okay, and then 90 degrees after that, you're at 720. So just continue your cycle. And then you're going to continue it for one more rotation. So complete the pattern one more time. So up to 810. Then 90 degrees over, we're back up at 7.5. 90 degrees past that at 0, and then finish at 1080, -7.5. I think I misgraphed that piece right there. Okay, so then you're just going to complete your graph here. Oh, I just put that in the wrong spot. There we go. What's wrong with it? Oh, it's okay. As long as it's not like a zigzag. What'd you say? Just make sure it's curved. Yours looks fine, I think. Okay, last one. This one's a little bit more challenging. Are we all okay with this one before you move forward? Okay, can I scroll? Guys, I'm seeing a lot of cell phones out. I don't know why I would be seeing that because I made my expectations clear every single day in every single lesson that cell phones should be away during lessons. So put them away, please. I don't want to see them. If I continue to see them out, especially during lessons, I'm going to take them. So store them away. I'm going to wait until I don't see them on desks. Yeah. Okay. Last part. Okay, so a Ferris wheel has a diameter of 15 meters. It's propped 6 meters above the ground at the lowest point. Assume that the rider enters a car from a platform that is located 20 degrees around the rim before reaching its lowest point. The wheel rotates counterclockwise. Model the height of the rider above the ground versus the angle of rotation versus using the sine function. So we're creating a sine equation for this. I think a sketch would help us first in order to create a sine equation for this one. So I'm going to draw a picture of what's going on here off to the side here. Here's our nice little Ferris wheel. We know that at the minimum height, how many meters is it off the ground? 6. Okay, so let's mark that. This minimum height will be 6 meters. If the diameter is 15 meters, what do we know about the max height off the ground? What would be the tallest or the highest that someone can go Okay, so max will be 21. What about like the middle height? What if I cut this in half right here? How high would that be off the ground? What would this be? 13.5 is correct. How do we get that? Okay, or because the diameter is 15 meters, we know the radius is 7.5 meters. So you can do that as well. So each of these heights are 15 or 13.5. Okay. So far, so good. We start, so if we're rotating counterclockwise, we're rotating in this direction. We start 20 degrees before reaching the minimum height. So if this is the minimum height, I'm going to go 20 degrees before that, which is like right here. This will be 20 degrees inside here. This is where I start. And that's before we hit them in, and we're rotating counterclockwise. So we're rotating toward the right. So this will be 20 degrees before we rotate.
Isn't that clockwise?
But I'm rotating this way, right? So that will be 20 degrees before we hit them in. So start is always 0 degrees. That will be my 0 degree location. I'm not sure exactly how high this is off the ground. I don't really know this height. I know it's probably close to 6, but I'm not sure exactly what that is. So at this location, it's at 6 meters, but I don't know how tall it is at this location. We can calculate it actually, because if I were to make a right angle triangle here, then if I find this, then I can just subtract that from 13.5 to get our starting height. What's this angle inside here? 70. And what's the length of this black line? How far does this go? That's also the radius of the circle, right? What's the radius? So it goes 7.5. So could somebody figure out what x is? Let's zoom in here a little bit. You tell me.
X is in.
We have hypotenuse. This. Oh, sorry. I guess maybe I shouldn't call that x. It's kind of like y. Maybe. Oh, let's go backwards here. We'll call it. I don't know. It doesn't matter. We'll call it a. So this is 70. This is 7.5. I want opposite, and I have hypotenuse. Which trig ratio can you use? Okay, so let's use sine. Sine of 70 equals a over 7.5 hypotenuse. So just multiply that 7.5. We want opposite, and we have hypotenuse. Does it round to 0.5? Okay, so what is, yep, 7.05. So what's this? If this is 7.05, correct. Yep, you're right. No, we don't have to do it for all of them. You can do it for one part of it if you need to find the starting height. We just subtracted this from 13.5 because this whole thing is 13.5 and we have this and we want this. Okay, so our starting height is at 0. We're at 6.45. How far do we rotate to get here? Oh, sorry, I meant to change color. Okay, to get to here. 20 degrees at a height of 6 meters. The rest should be pretty easy. How far have we now rotated to go up to this point here? Yes, just add 90 on, right? Because this is 90 degrees. So now we're at 110 at a height of 13.5.
Which question are you asking about this last year?
Like with the circle rotation? Yeah, probably. For the rotation questions, at least. Okay, how far have I rotated now? 200 at a height of 21. Next.
290. At height of negative 13.
Mhm.
Yeah.
13.5. We're talking about height off the ground here, so there's no negatives, hopefully, unless you want your Ferris wheel going into the ground.
And then 20. Or
And then we'll just finish at 360. So 360 back at the starting height. Okay, so over in our y-axis, this is going to be height off the ground in meters. And this will be our angle of rotation as we rotate around. We need to go up to 21. So let's go by twos here. And then we're going to just have to kind of approximate 0, 6.45, probably somewhere like right around here. 20. So this is actually going by 30s. This is 30, 60, 90, 120, 150, and so on. Oh, that's 300. Okay, and 26. So that will be like right about here. 110, 13.5. We're gonna have to just kind of estimate where these ones are. 200, 21. 290, 13.5. And end at 360 for 6.45. Okay, there's a little bit of room on the back. We're going to model this using a sine equation. So we're going to figure out what this is with a sine function. What did we talk about with amplitude and radius? What's the connection there? Well, what's the amplitude of this function? If the minimum is 6 and the max is 21, what's the amplitude? What? No. Good guess, but no. So max minus min over 2, yeah. Which is?
21 minus 6, 13.5 divided by 2, 7.
So what's the connection between amplitude and radius then? They are equal, right? So I can always find the A value by doing just the radius. A should be 7.5 here.
How is 13.5 diameter? Half of it, 7.5. Isn't it 7.
It's not. It's only because it's 6 meters off the ground. Half of 13.5 isn't 7.5. Half of 15 is 7.5. Yeah.
Why is 13.5?
It's okay, height.
Because we're talking about height off the ground. So we're talking about like this measurement off the ground on both sides. Okay, what is the C value? What's the middle in between 21 and 6? It's 13.5. Yeah, we already have it. It's here. This is the midline of our graph, right? That's the middle area. So C is 13.5. You could do max plus min over 2, or you can just look at that middle height that you've already found. Nathan? 21. Min is 6. Yeah.
Can you say m equals radius?
Yeah, that's fine. Okay, what's the period? How long does it, how many degrees does it take somebody to rotate all the way around Ferris wheel? 4? 360. Takes 360 to rotate around a circle, right? So how do I use that to find the K value? So if the period is 360, how do I use that to find K? K equals 360 over the period. So 360 over 360 gives us 1. So K is 1. And we're trying to find this as a sine function. So I need D of sine. What am I looking for? This is from the last lesson. What am I looking for when I'm trying to find D of sine? Rising midline. So from the midline, I penciled in our midline on our graph here. Where does it start rising? No, from the midline, 110, yeah, happens right here. So this is the D of sine. The X coordinate there is the D of sine. So it's going to be 110 to the right. Okay, so what's the equation? Let's call it H at X, height at some rotation of X. What should my equation look like? Let's put it all together. Was it? You're missing the shift though. What about that 110 right? Yeah, so we're going to put minus 110.
You have to write equation there?
Doesn't matter to me. Okay, and how would I change this if I were to express as a cosine? One quick change. Okay, and what is the whatever? And how do we find D of cosine? We could find with those little formulas that we talked about, we could do D of cos equals D of sine plus 90 over K. Or we can just find the max on the graph. Where does the max happen? No, like X coordinate of the max. 200. We can see it here as well, right? Okay, so it happens 200 to the right. So what should I put in here? Yes. Good. If you can do that one, you can do any of them. That one's like the hard version of. Yeah. So there's 3 things that the question might ask you about, right? Might ask you about vertical displacement from the center, horizontal displacement from the center, or vertical displacement from the ground, which is what we did in the last question. So look out for those indications. Just for homework questions, guys, if something doesn't tell you the direction of rotation, we're going to assume counterclockwise. Okay, so if it doesn't mention it, you can just default to counterclockwise for that. The C is the middle value in between the max and min. It's like this value right here. You can either look or you can do max plus min over 2, like 21 plus 6 over 2. Same thing. Any other questions? Okay.
Can I do it for now?